All right, hello and welcome back to Data Science Castnet. And today I'd like to talk about a kind of research idea or research thread that came up recently. So this is going to be a kind of mishmash video. We're going to look at a paper and then actually a sequence of papers that led up to that idea. Then we're going to talk about some new extensions of that idea that I've had and that others have had. We're going to try some of those in code, and then I'm just going to live explore from there. So I'll edit the video. We'll start with talking about the idea and or ideas and what that looks like. We'll look at a bit of the code, and then I'll pause and I'll just record occasional updates as I spend some of today kind of digging in and exploring this idea, and I'll show you how I go from like, oh, that would be neat if someone did that, to like, let's actually try this. Let's try and nail down what's the smallest piece of like quantifiable research we can do that validates whether or not this is a good idea. All right, so let's get started. The paper that sparked this is one called Model Extrapolation Expedites Alignment. And so we'll come and look at this just now, but I thought it would be helpful to draw kind of a through line through some of the pieces that I've read, or like the bits that fell into my head as soon as I started seeing even just like the abstract of this paper. Right, so I'm going to take you on that journey, that story, and then we'll get to this one, and then we'll talk about many other ways we can take the same sort of similar idea. So to start with, I'd like to cast our minds back to diffusion models. They were all the rage, right? Like think back to when the Glide paper came out, one of the first like open source models that really genuinely did some cool image generation. I'll show you the samples there, and we can kind of admire actually pretty darn good for the time, especially. This was kind of revolutionary. But anyway, this is one of many papers, but there's a piece that I'd like to highlight that they flag as being very important for their work, and it's this idea of classifier-free guidance. Now, this isn't the paper that introduced that, right? That was introduced back in 2021, Hohenn-Salomons. But I think this was one that, at least for a lot of the like image generation community, was like, oh, we have to have this thing. And there was a big sort of, is this a hack or is this like a genius idea? But the core idea is actually very simple. So we're doing this multi-step, in this case multi-step diffusion process, right? And at every stage we're predicting something, whether that's predicting what the noise looks like, or later diffusion models, different objectives, but we're making some prediction, right? And so we can either just generate without any other information, right? So we're just generating like arbitrary samples from our data set would be like your minimum basic diffusion. But that's not super useful, and this model was one that took in text. So instead of just generating, we can have generation with some conditioning information, right? The likelihood of, or our prediction, given this conditioning information C, which could be our text. And if we've trained the model sometimes with that conditioning and sometimes without, we can also say, okay, what is the like the base case? What if we predict without any caption, right? An empty caption. And we can then compare those two predictions. And instead of just using one or the other, we can interpolate between them, right? What if we took a 50-50 mix? But we can also extend further. So this formula here, don't worry too much about the details, but it's like, what if I took the prediction without any caption? Then I added a scalar times the difference between the prediction with the caption and the prediction without. Right, so if I was to draw this on a graph, I think this drawing tool works. Nope. Okay, don't worry about it. If we imagine a graph, we're moving from the point that's the no caption prediction to the point that's the prediction with the caption, and then even further in that direction, right? But we're doing this on the model's prediction, so all of these different multi-dimensional outputs, and we're moving further in that direction, maybe twice as far or three times as far, right? This guidance scale. So that was very popular, very effective, still used to this day in diffusion models. Now, it didn't take long for people to apply this. I found this paper, but actually I know several people, for example, Catherine Crossan, who is very active in the diffusion research, suggested this far earlier. This idea of what if we took the same idea applied to text, right? So we have some sort of text generating model that's producing one token at a time. What if we do classifier-free guidance on that? So we take the prediction conditional on possibly some prefix or not. I actually was kind of sad to find this paper just before I made this video, because this is one of the things like, oh, if someone hasn't formally tried this, we should try it. I definitely saw it suggested, but I hadn't actually seen it done his paper, so I actually hadn't even read the abstract until I started recording this video, but that's how it goes. Anyway, suffice to say, like, people have thought of this idea a little bit about text. One of the ones that I did definitely remember seeing when it came out was doing a similar thing, but taking a model, so this case working with a llama model, and contrasting different layers. So decoding by contrasting layers, DoLa. This is a paper that looked at the output probabilities for different words. If you did early stopping, right, you took the hidden states from halfway through the model and predicted based on those, versus if you let them flow all the way through the model. And what they noticed was that there was some facts. So this paper is very focused on factual information that only became apparent once you'd processed through the whole model. So here's an example. Where is the capital of Washington State? Now, Washington State, the biggest cities are Seattle and Vancouver, and most people, myself included, wouldn't know that Olympia is actually the administrative capital. So if you were to only go through the first 8 layers of the network and then predict the next word, the most likely next word would be Seattle. Likewise, after 16 layers, likewise after 24 layers, and even after 32 layers, the incorrect but likely next token Seattle is slightly more likely than Olympia, the correct answer, right? But you can see that there's a difference. The model does actually know, theoretically, or it seems like, that Olympia is actually quite a likely answer here, but it only figures that out by the 32nd layer. And so what this paper does is it says, well, let's take the difference between these two, right? And let's see which ones are increasing, and let's scale that difference, and let's use that as our final prediction. So it's an interesting paper. There's lots of nuance as to like which early versions should you use. They find all sorts of measures for like picking out how predictions change over the different layers and when you should choose and all of that jazz. But it's a fun idea, and I believe I did either a video or at least a write-up of this showing it in action. But it's very cool because it starts to give you some intuition as to how these models work. And we were chatting about this on a research call last night. And yeah, it's like, why does this happen? Well, the idea is that really early on in the network, right, you've got mostly the input token and its features. But slowly, as you process through, it's getting enriched by more and more from the context. And then separately, your MLP layers especially are in many ways kind of acting as like almost like a database, right? Like a lookup. So my hidden state comes through my MLP, and often it's hardly changed, right? The residual is most of what flows on through, and there's very little modification from any given like attention head or MLP block. But every now and again, the input set of features is enough to activate something and to modify it as it flows through that MLP block. So that's, people talk about that as kind of like a database lookup or adding relevant facts or relevant features. So you can imagine, like, okay, let's say we have some MLPs that store this information that Olympia is the capital of Seattle, right? So when I start out, like Washington State by itself might not be enough to activate those features. It has to be Washington State with the context of like asking about a capital that activates those features. And so initially, these first layers are just busy augmenting Washington State with some of the context, like, oh, this is in relation to the capital, and this is inside a question, and it's a question about where, and so on. But as we get to these later layers, hopefully somewhere in there are some MLPs that store this fact. And so as this rich hidden state passes through that's now been augmented, I'm talking about Washington, but specifically in the context of a capital, and I want Washington State, not DC, the Capitol Hill, like it's rich enough now that it's able to then retrieve from those MLPs, from those weights, this fact, right? And so as you flow through, you're getting these richer and richer features. They're retrieving more and more relevant other features until finally they're able to produce, hopefully, the correct answer. But you can see in this case they don't quite. And we can kind of like, okay, well, we can hope that by comparing the two, we could get there. Okay, so that's a paper that had been around a little while. We're going to eventually get to model extrapolation, but I do want to show one more paper, and I also want to talk about the way that I found this. So DoLa, I knew there was a paper like this, right? I'd made videos about it and talked about it, but I couldn't for the life of me remember the silly name, right? Because they said this one and these letters. Common paper naming thing. Anyway, so I fired up Paper Finder, Allen Institute Paper Finder, and I put in a query for, I said there's a paper improving factualness by comparing the predictions from early layers versus the final output, and then linearly interpolate to move away from the early ones. It might have been called something like DoLa or similar, right? So I knew there was something there, but I'd searched DoLa and DLoco and a few others, and I didn't get it. Anyway, so it went off and it did its paper search. This is a kind of like agenty paper search. It's doing some keyword searches, it's following citations, it's re-ranking, judging the relevance. It's found 6 relevant papers, it's sorting them, and it's coming back with these results. And you can see the second result is the one I was looking for. And they've scored this is indeed relevant. This exactly matches the criteria I gave it. They also found another one, Delta. And so this was cool. This was like a literature search for a paper I was looking for, but I also got some other relevant papers. And specifically this Delta one is great. You can see this is a very clear extension of DoLa, right? It's from March, so just last month, like just over a month ago. And what they do, you can see this figure kind of captures it. We're just going to look at the logits across the layers, but we're going to do a linear fit, right? We're going to like fit this regression line of like how are these changing. So if you look at the DoLa paper, that first illustration, you can see like Olympia is getting more and more likely and Seattle is staying roughly the same or getting slightly less likely. They say, what if we imagine what this would be on the 32nd or the 33rd or the 34th or the 35th hypothetical layer, right? What if we continue this trend and then sample from there? So yeah, really neat idea. I haven't dived into the paper fully to like check their work or anything, but you can see this is like a natural extension of this idea in DoLa, and more generally this idea like, oh, okay, you know, imagine like the early layers know much less than the later layers, right? So we compare the uninformed case with the informed case, and then we say, well, what if we even went further in that direction? It's very much like saying, oh, we have the prediction without the caption and the prediction with the caption. What if we went even further in that direction? And this general idea seems like one very much worth playing with more, right? Okay, so now that's like the lit review in history. Let's talk about the actual paper briefly, although then we're going to go back and our experiments aren't going to be on this paper. They're going to be more on some of these previous ideas. But okay, so this paper comes in with the framing. Look, we take these language models, we pre-train them, we do supervised fine-tuning, and then we do like alignment fine-tuning, right? We do some sort of RLHF, or these days something like direct preference optimization, DPO, but this can be computationally expensive. We have to spend money to do this alignment. Can we cut that down? So a little bit of a hazy justification, because actually like that part of the training is currently at least much smaller than the pre-training, but still, if we could do it even faster, that'd be great. Okay, so they introduced their idea of model extrapolation, and I bet just by the history you can guess what this is going to be. So we're going to take a supervised fine-tuning model, right? So this is going to be like our baseline, our starting point. And instead of doing the full DPO training, what if we could do just a little bit of DPO training and then push further in that direction, right? So let's go find some of the things here. Okay, so this is justifying like the difference between the pre-training and after a bunch of supervised fine-tuning. There's quite a large difference, but between that and your final like little alignment, it's just the cherry on the top. It's actually very little difference in the weights. And so they say, okay, if we can find the difference between the two, you know, all this hand-waving about Taylor expansion and stuff, but if you look at the formula, you're going to get to this point where we're saying, like, model 1 and the difference between model 1 and... Wait, where's the final one? Yeah, here we go. Some value times model 0 plus some value times model 1, right? So, like, interpolating between them, and then what if we put this larger than 1? Because if this was 0, we just have the original checkpoint. If it was 1, we'd have the RLHF model. What if we made it larger than 1, right? What if we went even further? And so they do some justifying. They say, look, if we vary this between 0 and 1, 0 being the like base model that we're starting with, and that's just been supervised fine-tuned, and 1 being the like RLHF model, you can see that the like reward score, the goodness, the alignment, whatever you want to call it, the measure that we're interested in goes up. And so you can naturally see like, oh, we're going to ask what happens next, what happens after that. And so, yeah, they do these experiments, and sure enough, they find out that cranking that number above 1 can often get you gains, especially if you've only done a little bit of training. So I'll go down to the money shot here. So here you can see this blue line, for example, is if we've only done 10% of our normal DPO training, right? That might get me to a reward of 4. what if I took the difference between the model before that training versus after, and I did that same difference again, right? So I used a value of 2. Oh, we get a higher reward and a higher reward, and as we like scale beyond that initial training, um, it peaks and then it falls off. Now, if we've done more training, taking the difference, we've now changed further, right? So it makes sense that this graph is compressed, but still scaling beyond 1, we still see an improvement. We still see like we're able to kind of get close to or even above the score that we would get with the full training if we weren't doing this extrapolation. And so this tells us a few interesting things. One, like this feeds into the discussion that a lot of this kind of quote-unquote alignment is actually kind of like a simple style shift. They're optimizing, let's see, I think it's like MT bench and alpaca eval. This is LLM as a judge, like basically style points. It's not like you're adding any new knowledge or crazy new capabilities to the model. You're just teaching it to answer in a certain way, right? A helpful, assistant-y way. And so the intuition there is that a big pre-trained model already knows what helpful assistant-y stuff looks like, right? It's got rich enough features to find that. So then the change that you're making is very small, and it's also like a well-defined vector. And so if we do a few training steps and we figured out roughly what direction we're going in, just naively like extrapolating that will get us an improvement. You see this also with like people tend to do LoRa, right? And so again, like, oh, LoRa works well for this kind of like alignment type training. And then that, again, like you can use a fairly low-dimensional LoRa adapter. So this is like a simple, like already existing direction potentially. And also you can then scale the LoRa weights, like change the difference that you're applying with the LoRa and see some impact. Yeah, so very, very cool, like the same sort of idea, right? We have something that pushes us in the direction we'd like to go, and then we go even further in that direction. And so there's lots of, complication and fancy terminology, but all of these things are basically that same idea. So cool paper, cool idea. Let's now talk about what this means, right? What do we take away from this? And I think what we take away is this general idea of interpolating either in the weight space of the models, or in the space of logits, or in the space of like noise predictions in a diffusion model. It's all hovering around the same cool idea. What if we contrasted one like bad prediction with a better prediction, or one badly trained model with a better trained model? And as soon as you're thinking in those very general terms, you've identified this general trend. It hopefully suggests a lot of cool experiments to you. So for example, you might be asking, hey, instead of using the early layers in Llama versus the later layers, what if we compared like the 7B model versus the 70B model, right? Or the 1B model versus the 7B model versus the 70B model. And we said, look, the 1B model is going to predict things based on like general rough, text likelihood. The 7B model maybe knows some more facts and it's got more interesting things. The 70B model, maybe that's, being able to think more deeply or pull in more like obscure references and find an even more correct answer. What if we just like extrapolated and tried to linearly predict, oh, like what would the 140B parameter model look like, right? If we did this kind of regression. So you could do like model size contrasting between this, like a small model and a big model. You could also do, and this is one that I'm quite excited about, like playing with different prefixes. So I have a model, I ask it a question, and I'll use an example here. So we've been working on a web framework called FastHTML. If you ask a language model about FastHTML, because that's something that's very recent and not very well documented on the internet, it'll say, oh, you probably mean FastAPI, right? So a base model is not very useful for getting help on FastHTML. But if you give it like the concise reference guide, and you put this in context, and then you ask it about FastHTML, well, it's more likely to give you an answer about FastHTML versus FastAPI, right? But still, even with this context, we've noticed sometimes, it's still going to default to the way things have been historically done on the web rather than like the FastHTML version of that. And so that's another thing I can imagine. Rather than a small model and a big model, what if I gave one model no context on FastHTML and one model a really good long context about FastHTML? And if even that wasn't enough, what if I just did this extrapolation, right? So I'm taking the difference in logits for those, and as I'm decoding, I'm pushing more in the direction that it would answer if it was really paying attention to that context. as opposed to like only maybe vaguely paying attention. So that, yeah, those are just like a couple of ideas. I'm sure you can think of more. You could imagine like training a model on dangerous completions versus good completions, and then going like with a negative scaling away from the dangerous model. Right? You can imagine like all sorts of ways that you could get a good version and a bad version and then push even further towards the good version. So I'm not saying this is the best way to do this. You could probably just train for longer on the good stuff and get a good model. But it is an interesting one to explore. So now let's talk about like how do we actually test that? How do we try some of these ideas? And I'll show you like my first 10 minutes of code before I started recording this video, playing with this exact idea. Okay, so let's go look at the code. So I have here a Google Colab notebook. We're importing PyTorch and Transformers library, and then we have some basic setup, right? Getting the next token logits given a model and some inputs and so on. So the logits is like the raw outputs of the model. For every possible token in the vocabulary, it's assigned a score, and then we're going to use these later when we're generating. And so then I have this contrastive generate function. It's going to be getting the logits for two different versions of the model, right? Either two different size models or the same model but with different prefixes. And then we're going to do exactly the same formula as Classifier-free guidance, exactly the same formula as the DoLa paper, except instead of being the logits based on middle layer versus last layer, these are just based on like whatever two models we've passed in. We're going to use this alpha value to scale between logits 1 and logits 2. And we can use alpha greater than 1. Once we have these logits, these scores for different possible next words, we can scale them by the temperature, which is just standard language model sampling, turn them into a set of probabilities using the softmax operation, and then pick the next token from that distribution. We could also just take the one with the highest score if we're doing so-called greedy decoding. Okay, so this gives us a way to take two models or two variants of a model, either different contexts or different sizes, and to combine their predictions together using this kind of like interpolating / extrapolating technique and pushing them in the direction of one versus the other. Okay, so let's try this. Doing some initial testing on GPT-2, but we'll scale up very quickly to Llama and so on. And actually, let's go straight to running Llama. So, okay, here's a... Sorry, you can... I'll share this notebook. It'll be a lot tidier than it is now. But here's an example, right? So we have Meta Llama is our model. We have a prompt that says describe a perfect summer day. And for one of the models, we're going to give it this extra style hint as prefix in the style of Dr. Seuss, right? So with alpha equals 0, we're using the model without that prefix. Describe the perfect summer day. I'm not sure I can do that. Summer's my favorite season, but I also love winter. Waffle, waffle, waffle. Okay, alpha 0.5. So this is like in between the two. Describe a perfect summer day. You wake up in the morning feeling fresh and bright with the warm sun in your face. It's like, oh, okay, that's nice. It's different to this. And maybe that's what you want, right? You only want the like 0.5% helpful model, sorry, or 50% helpful model, or the 30% Dr. Seuss style model. Alpha equals 1, so this is now just the one with that style prompt. The sun was shining bright and bold, with warm on skin, young and old. It's doing a pretty good job. But imagine this wasn't following the style enough. We really wanted it to be really Dr. Seussy. Well, what if we use a scaling of 1.2? Perfect summer day, that's truly divine. The sun shines bright with warm and fuzzy glow. Okay, so this is a very small model. This is like a very initial test, but it's kind of working, right? I can see that at alpha 0, we're not getting any Dr. Seuss, and at alpha 1 and above, we're getting more Dr. Seuss. And you can try this on a few different things. You can try like fact injection. So here is on GPT-2, who discovered penicillin, and one of them gets some context that gives it the answer. And this is a very old model, very dumb model. So let's go to the penicillin one. Here we go. Yeah. So who discovered penicillin without the hint in 1878? Alpha 1.5, the first of its kind in the world. It's just like this is like just base model silly generations. Okay, but at alpha 1, who discovered penicillin? Alexander Fleming. It's got that context. Or 1.5, it's even better. So again, not a great test because we could just use the model with the context, but I feel like, yeah, we should mess around with this and see if there's something more quantitative that we can pick out and if we can see a general improvement versus just like a funny toy. So there's a few ways I'm going to do this. One, scale this up to slightly larger llama models and try just some very subjective tests, right? More kinds of thing like this. Maybe like give it a sample of some writing as the context and then push it in that direction with some scaling and see if it gets more and more like that. Very like, am I on the right track? Are there bugs in my code at all? And I feel like we're almost getting to this point where we've satisfied ourselves. Nope, the code is kind of working. And then it's like, okay, how do I turn this into a quantitative test? And so that's going to be the tricky part. That's what I'm going to try and figure out over the course of the day. It's going to put in updates in the video if I get anywhere useful with it. And yeah, that's something maybe that also, if you want to take homework, you could pause the video here and say, look, I'll get the notebook, this like rough initial code from the description, and maybe I'll try running with this myself. And finally, I should talk about like, okay, so I've got this notebook and I've got this code running. You might notice it's not written in Jono style, and that's because it's not written by me at all. 10 minutes before from having this idea, right? I woke up, oh, maybe I should spend a bit of time today doing this rather than like my actual work to-do list. I hit the Windows key and H, which starts voice dictation, and I explained the idea. So say I want to try the sampling strategy, contrastive extrapolation, you comparing these predictions, blah, blah, blah. I just described what we've been talking about to Gemini 2.5 Pro, and bang, it spat out. I said, put this in code, nice and clear, let me do it in a collab, and it spat out the code that I've been using to do these initial tests, right? And it's just like a highlight of, this is nothing crazy, right? This is like well-known-ish pieces, getting the next token logits and decoding, that I could totally write myself, but it'd take a little while. Really, really nice to be able to get a starting point. I definitely would like to check through, especially the key parts here. Make sure that it's doing what I think it is, but like you can see the important part. This is the important part. This is like not supported anywhere existing, but it's also like concrete and obvious and easy to verify if that's exactly what you described and you carefully described it. And then we can test it and we can check it out. So yeah, just like putting it out there how useful LLM assistance is, as long as you're like willing to also shepherd it and test it, use somewhere like Colab where you can do this iterative like testing and make sure everything's working. So yeah, I guess what I'm saying, like I'm not saying, hey, just let the language model do all the coding for you, but I am saying like, hey, if you've got an idea and you don't have a lot of time to explore it, you know, between like waffly voice noting out my initial idea and like running a prototype that I can see is kind of working, literally like 9 minutes. So I'm very impressed by Gemini 2.5 Pro. I'm very impressed by language model assistance in general for this kind of research. And as I go through today, I'll definitely be like back and forthing with different AI assistants on, you know, particular experiments or tidying things up or maybe adding explanations so that hopefully by the end of the day we've got, you know, an interesting result and a write-up and this video for anyone else who's interested in this particular quirky little question. So I'll pause the video now, and then if you see no more segments in it, this is kind of like a exercise left to the reader, but if you do, that means I'll be adding ones as I make progress. Cheers for now. All right, we're back. Okay, so when we left off, we had this kind of messy, mostly Gemini written notebook that was like proving out the concept. So what I've done since is create a new version, so I'll share both of these in the chat and any future ones. A little bit of explanation, highlighting what the core thing is that we're doing here. So if I come back to this, or if anyone else wants to come to this, you've got a bit of more like context of what this notebook is showing. And then it's some of the same code, but broken out and tested piece by piece and explained. So we've got our imports, we're loading up the models, we're using the sampling demo from the model code just to check can we sample. And you'll notice here there's a difference. We're using a chat model, we're using tokenizer.apply chat template, right? So we now can specify messages with a system and a user, but we can check like what's actually going on. Like let's still use our previous code for getting the next token logits. We can get some IDs, right, and decode them and check this is what that chat template looks like. There's a begin of text and start header and system and so on. But you can see in there is our you're a pirate chatbot. They also add today's date for some reason. I guess that's part of the template. there's our question, there's our answer here, starting in assistant Arshif Mitimbers name be Captain Chat. Okay, so we have the models loaded and they're producing reasonable outputs when we give them a default prompt. And importantly, we can get the logits from them just like before. So we can look at the logits from model 1, which is llama 3b instruct, and model 2, which is llama 8b instruct. And you can see that in both of these cases, if I stop it right here, I'm the scurviest. Pirate is the next choice, but for model 2, the sort of more advanced model, it's less likely. So we're getting two sets of probabilities here. And so we can ask, what if we extrapolated? What if we pushed further in the direction of model 2? What would the likelihoods look like then? You can see pirate is now way down, and we've got chat and sk, probably for scum of the sea or something like that, starting to get, so you can see there's a distribution shift. So we're validating our core idea here. Am I getting new logits that are different to either of the ones from each of the models by mixing between these two with this alpha value? And you can try, what if I set alpha to 0? What if I set it to 1? Will I get the original predictions that I'd expect? Okay, and so then I've taken the generation thing and cleaned it up a little bit. There's some pieces we don't need. I thought for this one I'd focus just on 2 model sizes rather than messing with the different contexts. So we're going to be comparing model 1 and model 2. They have the same tokenizer. We're going to pass in the messages and we apply our chat template in this function. And then we're running through, starting at the end of the input, for some max new tokens, getting logits 1, getting logits 2, combining them, sampling from that distribution, checking if we reach the end, and if not, carrying on the loop, right? So we can test this out, system, content, same as before, like set some messages and use our generate function rather than the Hugging Face one, and sure enough, we get some reasonable text out. You're looking at for a bit of info matey, etc., etc. Okay, so this is like setting up, can I load 2 different models? Can I sample from them with this special, contrastive, extrapolative sampling magic? Let's do an eval, right? So this is GSM 8K. I'm loading the data from OpenAI's GitHub, and you can see here's the first one in the data set. Natalie sold clips to 48 of her friends, and then she sold half as many clips in May. How many clips did she sell altogether? This is a gold standard explained answer, and then you can see there's the separator and then the final answer as an integer. So yeah, that's the type of question that's in this eval. I'd encourage you to do this step by step. First get the text of the response and then load it into JSON, line by line, and check that it all works. But because I've done this before, I'm just going to blaze through it. So the way we'll feed this to our model is still to use the chat template that it's been trained with. So we'll say, look, answer the following question, end your response with final answer, and then your answer. We just want to make sure that the last number in this response is going to be the correct answer. And we can feed it the first question. We'll see that it does its own little exploration. And so then it gives us its final answer, and it ends with the final answer. Okay, so we have a way to feed this to our model, or in this case, our sampling thing with 2 models and generate answers. We can extract the answer out just using a regex to look for the integer part of whatever the final number is the thing that I'm looking for here. So we'll extract out just 72 from this text, or a text that looks like this. Okay, so before we run on the full eval then, sanity check, running through 10 questions, getting the question and the answer, where the answer is just the final integer part of the answer, then getting the model answer with this function that we just wrote, and comparing them. And if they're correct, then we keep track of that, and if it's incorrect, we're going to print which number we're on, what the question is, what the model answer is, what the true answer is, and the answer text that the model produced. This is nice for debugging. You can see here there's a question. He writes a 3-page letter to 2 different friends twice a week. How many pages does he write? The model answered 312. The correct answer is 624. You can see the model's reasoning here. It is producing a final answer, and that is getting extracted. So our part of the eval isn't working. It's just the model genuinely made a mistake. It says 3 times 2 per week, but it's actually 2 different friends twice a week. So it would be 3 times 2 times 2. And so the model's made a genuine mistake there, but it got 9 out of 10 correct. So it gets a score of 90. If you run this, that might be 70. So that's the setup to say okay, can I do this technique that I thought of? Can I check that it's all working in smaller chunks that I can understand? Can I test it out on a few and manually examine the errors? All right, I think we're about ready to say, look, let's go through the different alpha values now, and let's run an eval. Let's give it 100 questions, just the first 100, right? Let's get the question and the answer, get the model answer, check if it's correct, and keep track. And so hopefully, this is like we're testing a hypothesis. We're saying the small model will be worse. So for alpha equals 0, we'll get a score. And then for alpha equals 0.3, hopefully the score will be slightly better. For 0.7, slightly better. For 1, we'll get the same score that we'd expect if we just used Llama 3 8B, so the larger of the two models. And we're very curious what happens at alpha equals 1.2 and 1.5 and 2 and 3. Does that score continue to increase and then fall off? That's what I'd predict. But who knows? It could be that this completely falls apart. If this is interesting, we can always increase this number here. We can try a much sort of finer grained range of alphas. But you can see, like, I just want to validate this hypothesis as quickly as possible. Like, let's load up two pretty small models. Let's use an A100 so the sampling goes quickly. This is still going to take a while, so I'm going to go back and do my real work now, probably while this runs. But in my head, I'm picturing this plot, right? I'm picturing this, like, ooh, from alpha 0 to 2, like, oh, increasing, 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 increasing. Oh, it's like beating the 8B model by doing this like special contrastive speculative extrapolation sampling, magic paper idea, and then it's going to fall off, right? And so that's the kind of like the hope. And of course it could be wrong. This could fail and we could keep tweaking it, but that's my idea. I've got this like, what is my smallest test of this idea of contrasting a small model with a big model and extrapolating further? Is this even a sensible idea? We've come up with a way to do the contrastive extrapolative sampling. We've come up with like a minimal eval. We're running it and we'll see. So I'll update you once this gets me some scores. All right, next update. I've actually stopped this. So we started at alpha 0, so just the smaller model, 73. Then it kind of dropped a little bit to 72, and then it went all the way up to 77, and then back down to 70, and then 68. So something's funky. And I was scratching my head about it a little bit, and then I realized, like, okay, wait, what models was I using? I was using Llama 3, just Llama 3 8B, but Llama 3.2, 3B. And so this is like, okay, mistake number one, those aren't actually super comparable. I think model Llama 3.2 made a bunch of improvements, including on GSM-AK, over the previous Llama 3.1 and Llama 3 versions, although they also didn't release all models in all variants, right? So big mistake there to use use two different models that aren't just different like size-wise, they're also different generations of post-training. So my mistake, what I've done now is set the Quen models downloading. So now you're going to use Quen 2.53b and Quen 2.57b. Alright, I actually cut there. There's some difference between the 3B and below models and the 7B and above models in terms of tokenizers, so I've just switched to using the 1.5B versus the 3B model for now. I was going to try the 7 and then the 14B, but I realized the whole point of this is to get a like minimum test, validate the hypothesis, small scale. We can always ramp up later, but for now it's all about speed. So I switched over to those two Quen models, and those are going to be the ones we compare. Checking that it all works again with the other stuff. And then it's been long enough now that I've actually forgotten where we were. We were running, we're looking at for different alpha values. Somewhere in the middle, alpha 0.7, not as good as all the way at 1, but at 1.2, the score's even better. This is only running on 50 samples, so definitely take with a grain of salt. Alpha equals 0, score 64, so I need to run this on some larger larger data set, fuller. I did try, part of the reason it's delayed, I had some work, but also I tried creating a batched version, because one of the obvious things is why we're running, like 4 single sample at a time, getting the answer. And I didn't really feel like writing that myself. I had a nice big lunch, sadzanya moriwo, for the Zimbabweans will know how sleepy that makes you. So I was like, oh, surely this is a good thing to offload to a language model, but I tried all of them, just about. I tried Grok 3, I tried Gemini 2.5 Pro, I tried O1 Pro, tried Sonnet 3.7 with extended thinking, and they all weren't quite there. I believed for a bit that Grok's code was running after a few tweaks, but the scores were pretty low. and several of the others struggle to get anything at all. And the reason is this is actually like non-trivial to do this kind of parallel sampling, because if you're generating for a whole batch, your questions are going to be different lengths, so you need to figure out whether you're going to do padding and how you're going to do that. You need to add attention masking, which at the moment there's no attention masking in any of this because it's all like single sample. And then you need to handle like the fact that we're decoding up to like say 300 tokens at a time. Some of them might finish early, and then after that we need to be doing padding, or managing that somehow. If all of them finish early, we want to stop. So anyway, it's just the kind of thing that's like suddenly going beyond the kind of, there's lots of examples of this on the internet type task, to something like custom and tricky enough that even the best reasoning models seem to struggle a little bit with this particular thing. And so I was mentioning this to my friend Jeremy, who said, hey, like, maybe that's a good signal that if you're doing something and the language models are really struggling, that's even more incentive that you should be writing this up. You should be, if I do spend the time and do a batched implementation of this, I should make sure I put it up online somewhere, because it's a good chance that someone else might be struggling with that as well. And something like this, this like batched inference, in interesting ways, and pretty much no one does that, right? Everyone just uses the Hugging Face generate methods, and doesn't really dig in, and if they do, it's kind of a little bit obscure what's going on, or they rely on something like VLLM. But it's actually like, when we look at our single case, it's not that bad, right? Like you're feeding the tokenized input through the model, and then you're getting the logits, and you're turning that into a probability, and then you're like sampling from that. Obviously, like there's different sampling approaches, but yeah, just doing this carefully and thoughtfully for a batch of things that are possibly different lengths, and sampling, some number of tokens past that, still, it turns out tricky enough that, a batch version of this just isn't like one-shottable as easily as I hoped it would be. But anyway, I might just run this overnight instead. I'm very eager. Like, I got an early result with Grok's possibly flawed batched version. Like, oh, this, the graph shows what I want. It's tempting to just publish it, but I think I'll benefit instead from ending the video here, running this overnight to get the full results on like a proper set of data, maybe working, depending on how much time left before I need to do other things, on a batched version so that at least goes faster. But yeah, I think I'll wrap the video there. So I've added some good ideas for future work into this notebook, right? Try more thorough evals. The full test set of this, or lots of other evaluations would be interesting. Try different size models, maybe try some larger ones if you have access to that kind of compute. If I don't get to it, definitely work on batched iteration, batched inference, so you test out ideas quickly. What about reasoning versus non-reasoning models? What about a midpoint in between? How good is that? Try different prompt prefixes and scale up and down for those. Revisit DoLa, using the early layers as the sort of worst model. Try this with different LoRa adapters, maybe scaling the adapters or just scaling the logits like we're doing. Maybe train a dumb LoRa and then extrapolate away from that. Train an unsafe LoRa and then extrapolate away from that or towards that. Could be kind of fun. Yeah, just think of any other cases where this like bad to good extrapolation might be applicable. I'd love to hear about experiments that you're running and ways this works out. So please do let me know about that. The only other thing I'll add is like, okay, while this is running, I've been on a call most of the time, but the other thing I did while I was waiting for some initial results is spend a bit of time just polishing this up into a little blog post, because even if it's a small little experiment like this, it's so valuable for everyone else to have things out there. Like I try and write up these little experiments, and it's so easy to feel like, oh, this is not worthy, right? I'm checking if some models can rhyme, or I'm poking at some like quick little experiment and I really didn't have time to do much. It's such a useful thing for everyone else. Like, I really enjoy whenever I see anyone, even if it's just like a little note, hey, I tried this thing, or here's my idea. It's so worth getting it out there, and it doesn't take much time. Like, I just dump in, here's the idea and the thing that inspired it and some past work that I looked at, and here's what I found, and here's the key bit of the code. Doesn't have to be polished, doesn't have to be fancy. Chuck in a few screenshots. You can see I've got some speculative results in there. I'll make sure to like actually put in the correct things once the experiment finishes. But yeah, my point is, if you're running something like this, definitely worth spending the time tidying up your, artifact, the code or whatever, tidying up your results, spending a bit of time making a little blog post, so much better than just doing this in a silo. So let's all, yeah, do some research together. Sorry if this is a little long, rambly video, but I hope you've enjoyed the experiment and that this inspires you to go and play yourself. See you in the next one. Okay, I can't end the video there because we have some results, and they're negative results. So I finally ran the code on 600 samples rather than the 50 or whatever we were using. Ran that overnight on my local graphics card, and you can see from the small model, interpolating between that to the big model, we do get this like gradual increase. But as soon as you go above 1 on that, start extrapolating past that, womp womp womp, the scores kind of drop off again. And so we were doing this in the Google Colab. We had this little hopeful bump past 1. A couple of the other early plots had something similar, but that's the thing when you're doing 50 or 20 questions that involve some reasoning and then some hacky regular expression to pull out the answer. This is a very noisy eval. And so just wanted to show that. I actually even then wondered what happens if I run this on a larger scale. So I also ran I ran on Quen 2.57b to 14b, a little bit more noisy, all actually like very similar scores, very little deviation, but gradual increase to alpha equals 1, maybe a slight increase to 1.1, but you can see like even the differences between nearby points just due to the noise and luck of getting 1 or 2 extra samples correct, kind of dwarfs any sort of signal here. So yeah, I would call this basically a null result, but still important to write it up in sample. And who knows, maybe there's other cases, more factuality focused benchmarks versus reasoning, whatever, where this might show an effect. But yeah, I just wanted to put this in to make sure that we wrap this up rather than ending the video sounding like, oh, this was going to be like some cool useful thing. Nope, this is like most research ideas that seems like, oh, maybe it's not going to be something amazing, or at least not right off the bat. Someone else could work on it for a bit longer and maybe find a case where it's useful, but I'm kind of happy to like get some closure and call this done, to be honest. I will flag like the final little bit of technique that I used for running this larger one. This has already gone past, like I've spent a few hours plus a few more like keeping an eye on the logs in the background on this. It's more than I wanted to spend, so I didn't really feel like spending a lot more time, writing a careful batched one and loading the models, quantized and carefully to fit on my machine or anything. And so I used something called Modal. I happen to have some credits where you can set up a Modal app, tell it what GPU to be on, max number of GPUs you can do, give it a timeout. And I didn't write this code. I just said, here's my script, Gemini 2.5, could you make a modal version? And I could run it on the same models as I'd run before and validate that the scores roughly matched, and then I could run it on my larger models. And so then that runs kind of in parallel for the different values of alpha, gets me back the scores, runs one GPU for every experiment basically, and pulls them together. So very like flagrant use of probably about like $60 or $80 of compute. Like I said, luckily I had some credits left over for them, but I just wanted to like point that out as something you can do if you're willing. The first experiment was let me leave this running overnight, right? Like there's a lovely scale where that works, and then above that there's a scale where like, oh, I can trade money for time effectively and say I just want to do one more run, get all my results as quickly as possible, in like an hour or two versus like waiting multiple days to run these larger ones. And so for running this one, just offload it to the cloud, run it on 9 H100s, one for each data point, and call it good enough. So anyway, nice little trick, nice if null result. I'll write this up. Got my post edited to definitely make sure the previous happy wording around how good it was is removed, and instead with the note that it's like maybe a null result, including the full code that I used to get this graph. Anyway, I really will end the video here. Thank you so much for watching, and we'll see you in the next one.